All right, we'll start with now talk number 2. Thank you, Akshara, for agreeing to give a talk today. Akshara is a senior grad student in our department, in our program, and she will be talking to us about her most recent work on harmonic maps. Thank you.
Hi everyone. First of all, I would like to thank my fellow AWM members and Professor Leviska for giving me another opportunity to give a talk at the student seminar series. Today I'll be talking about minimizing fractional harmonic map. Yeah, so feel free to interrupt if you have any questions. So first, let me introduce what is a harmonic map. So a harmonic map is a function from an n-dimensional domain in Euclidean space into a manifold n. That is the critical point of the Dirichlet energy that is given here. So this is nothing but the L2 norm of the gradient squared, and we call it as a minimizing fractional harmonic map or minimizing W1P harmonic map if this map attains minimum energy among all the mappings which has the same value on the boundary. So as you can see here, a minimizing map is a critical point. That means it's a harmonic map, but not vice versa in all cases. Also, if you want to think about as a physical interpretation, harmonic map in dimension 1, this is nothing but the geodesics. And we know that they are smooth. Now, let's look at the properties of harmonic map because it's a minimizer of this energy functional. If we look at any test function phi which belong to CC infinity, that means it's a it's a smooth function with compact support. And look at fix u and phi and look at the functions u plus t phi for any t which belongs to R. So since U is a minimizer, among all these mappings, U attains the minimum value. So you can think of this as a one variable function in the variable t now. Therefore, the derivative d by dt at t equal to 0, 0. Now, if we do the computation, we see that a few steps show that once you solve this PDE, we get Laplacian of U equal to 0. Therefore, if you have a minimizer that satisfies the equation Laplacian of U equal to 0, it's a solution to this PDE. And now here we looked at maps which goes into R or real valued functions. Therefore, in this case, any solution to this PDE is also a minimizer. Now let's change the case when you look at maps which goes into a manifold. In this case, I take the unit sphere. And we look at the same energy functional and look at minimizer of this energy functional. Now, our aim is to compute the regular Lagrange equation corresponding to this minimizer. So we look at a class of functions or admissible functions here, u plus t phi divided by mod u plus t phi, because we have to have maps which go into the sphere. Now, if we look at the derivative d by dt at t equal to 0, since u is a minimizer, this derivative is equal to 0. And further computation shows that the minimizer of this energy functional satisfies the PDE Laplacian of U equal to minus mod gradient U square U. So this is a nonlinear PDE with a non-zero right-hand side. And the moment we change the range of the function, you have a different PDE. And not that on the right-hand side of this function, assuming that we start with a function u belong to W12, we can see the right-hand side is an L1 function because u takes values in the sphere. So the right-hand side is an L1 function. So we don't have, we cannot apply Calderon-Zygmunt or Schroeder estimates to say further regularity. And also one thing to note is that in this case, the minimizer is a critical point or it satisfies this PD, but not vice versa, unlike in the Euclidean case. We can also do this for P Dirichlet energy, where you have the energy given by the LP norm of the gradient to the power P. And here we get the equation P Laplacian of U equal to a nonlinear term on the right-hand side. Some background on the study of harmonic maps. So as I mentioned before, in dimension 1, it's just nothing but the geodesics. We know it's smooth. In dimension 2, harmonic maps are in fact smooth. This has been done by Riviere and Helen by two different methods. And once we change the dimension from 2 to 3 and greater than or equal to 3, Riviere has provided examples for everywhere discontinuous harmonic maps. Um, and partial regularity of stationary harmonic maps, which are the interior variation of the Dirichlet energy. This has been done by Evans, and study on the singular set has been done by Whitwell. And there are results on minimizing harmonic maps from Sean and Uhlenberg. They also can be applied to dimension 1 and 2. Our focus today would be on um, results from Hard and Lin, where they proved minimizing mappings between two manifolds, Riemannian manifolds, are locally Hölder continuous outside a singular set. And this is their result. In this very specific case, when we have the manifold, the domain as the unit ball, and the range as the unit sphere in R3. So not that we discuss the case in 1 and 2. So we look at the case when n greater than or equal to 3. Otherwise, it's smooth. And we have a condition on P. P lies between 1 and n. And we look at if U is a minimizing W1P harmonic map, that means it attains a minimum energy among all the mappings with same value on the boundary. Then they proved that U is locally Hölder continuous in the domain outside a singular set with host of measure of the singular set equal to 0. And they also measured the dimension of this singular set, which is n minus p. So to understand the theorem, first let me give an example to see what's going on. So we take the case when our domain is the unit ball in R3. It's given here, and your range is the unit sphere in R3. And look at the case when p equal to 2. That means you have the L2 norm of the gradient as the energy. And uh, let's look at this map, x by mod x, the simplest one we can think about. In fact, this is a minimizer of the Dirichlet energy. And it has been proven by Scholl and Uhlenberg in 1982. That's the minimizer. And the singular set of this map is nothing but the zero set. So the dimension of the set is, it's a zero-dimensional set. And as per the theorem we had before, it's n minus p here. And in this case, it's much better because your n is 3 and p is 2. So it's better than what we expected. So today the focus will be on seeing the same result in fractional Sobolev space. What can we say about minimizers of the fractional energy? Before that, we define what is a fractional Sobolev space. For p strictly larger than 1 and greater than or equal to 1 and less than infinity, and s between 0 and 1, we define the fractional Sobolev space as follows. We take omega as an open subset of Rn, then the class of function WSP omega Rn, we call the fractional Sobolev space, is defined as a set of functions with the norm here. This is a fractional Sobolev norm given by the semi-norm, which is given in red color, plus the LP norm of the function. And if this is finite, we call this function belonging to WSP. And the semi-norm here is also called the Gagliardo semi-norm. So in the previous case where we had W1P, we had the LP norm of the gradient here. Now in the fractional Sobolev space, we have this double integral. So you can think almost as like the fractional derivative. We also define the space W dot SP as a set of functions which locally belong to LP, which has the semi-norm finite. So this class helps us also to include the constant functions. Now, just a quick look into the main theorem that we'll be discussing today. So we have some conditions on S, P, and N, which we'll be talking more later. And let omega be a bounded domain in Rn with smooth boundary and n be a unit sphere in Rn. If U is a minimizing WSP harmonic map, then our aim is to prove U is locally Hölder continuous outside a singular set with host of measure 0. I'll define what is the meaning of a minimizing WSP harmonic map later. Also, just keep a note that the dimension of the singular set here is n minus sp, strictly smaller than n minus sp, which is an improvement. So let's look into the idea of the proof. So I'd like to discuss the proof in the local case, which is easier to see and to see what's going on. So the key step involved in proving the result is observation that the minimizers follow a decay estimate. That means this normalized energy decays as R goes to zero. So precisely this is given as the decay estimate um, for any precisely for any theta belong to 0, 1/2, we can find an epsilon such that for any point x naught and radius r, if U is a minimizing WSP harmonic map, which such that the normalized energy around that point is less than epsilon to the power p, then we can bound the energy on a ball with smaller radius or radius theta r. Theta is smaller than 1, so theta r is less than 1. So that's why it's called the decay estimate. Um, Suppose for now, assume that we have the result. How does it help us? So once we assume there is a decay in energy, that means we can go to a smaller ball and the normalized energy is still bounded. Now we can do an iteration on this result. That is, you can take the new radius as theta r and repeat this procedure to get a bound on the radius theta square r. And after k iteration, you can see the normalized energy on the ball with radius theta to the power kr is bounded above. So this will help us to, we can reduce the normalized energy on smaller and smaller balls. So it's not surprising if I state that we can bound this quantity by a constant that is just depending on the theta. So this is like the normalized energy with a small variation in the exponent. And it's like you take the ball bx naught r by 2 and take any ball inside that, this energy is bounded. So why is this helpful? Because of an existing result which is called Campanato's theorem, which states that if you have an LP function and for some exponents lambda n and p, if you have this quantity bounded, then f is locally Hölder continuous in omega. So in our case, we have the gradient being bounded. As we see here, the gradient is being bounded. So here it's LP norm of the function, but we can use Poincaré's inequality to bound the LP norm of f minus average value of f and then get the desired result. So we proved that if you start, so this was our initial assumption that we had. So we took a point and then we had this initial, or not initial, we had this bound on energy. And then we proved that the function is Hölder continuous around that point. So now all remaining to prove is if you take all points where we don't have such a bound on energy, if that belong to a singular set, we are done. And it's given by Frostman lemma, which states that if you have a p between p strictly greater than or equal to 1 and less than infinity and some exponent alpha in the set, and if we have an f1 LP function f, and if we define the set x naught where this integral is lim sub integral is strictly greater than 0, then the host of measure of the set is 0. So this is exactly the set that we were talking about. So if it's not strictly less than epsilon, then that belong to the set, and those points are set of that set where these points belong has measure 0, and we can also explicitly measure the host of dimension. So that completes the proof in the local case or W1P case. That's the idea of the proof. Now our focus is on the fractional case, and here we define what is a minimizing WSP harmonic map. We call a function u belong to W dot SP a minimizing WSP harmonic map if for any function v belong to WSP with v equal to u outside omega, we have the fractional seminorm of u bound is less than or equal to the fractional seminorm of v. So this is like the fractional energy, u attains the minimum fractional energy among all the mappings. And just to recall the main result, uh, our aim is to see that if you have a minimizing WSP harmonic map, then we need to prove that it's locally Hölder continuous outside a singular set. So here, just let me focus or point out to the assumptions on S and P. So we take any P which is greater than or equal to 2 and less than infinity, and S between 0 and 1. And we have this additional assumption that SP is close to N. So I'll talk about this, where this arises when I discuss the proof. So some key steps involved while we shift from the local case to the fractional case. One important lemma is the Cacciopoli type estimate, which we need to prove. Assume SP is strictly less than n and P is strictly less than n, and assume that U belonging to W dot SP is a minimizing WSP harmonic map in omega. Then for any radius rho greater than 0, such that B6 rho is contained in omega, we have this double integral, which is like the fractional seminorm, but the outer integral is on B rho. This is bounded above by a constant C, rho to the power minus SP, and integral over B6 rho, the P norm of U minus average value of U. So here the constant is independent of the functions involved or the domain. And this is called the Cacciopoli estimate, and it's helpful in proving the decay estimate in the fractional case. So for proving the Cacciopoli estimate, we need something called the extension theorem, because we are going to multiply the minimizer with cutoff functions that will take the function out of the manifold. So we have to bring it back to the manifold, and we use an extension theorem to do that. Suppose you have a function which takes values in Rn or Euclidean space, such that it belongs to the manifold outside the domain omega. Then there exists a function W which takes values into the manifold, and it has the same value as V outside the domain. And also we have the fractional energy of W is bounded above the fractional energy of V up to a constant. So this is necessary for us to prove the decay estimate or the Cacciopoli. And I would like to give some background on the extension theorem here. So W12 extension property of W1/2 maps into simply connected manifolds. This has been done by Hard and Lin in the original paper, and they also did it for P minus connected manifolds with Kindler. And there is works on WKP maps for manifolds with sufficiently simple topology by Kitzel. Here K is greater than or equal to 1, not our case when it's WSP. And there are works on W22 maps into unit sphere and also extension. And there are many results about the extension of traces for Sobolev mappings into manifold by Schaftingen. So unfortunately, we didn't have a result on the extension of WSP map, which we had to work on. Now we have a similar decay estimate as the local case, which is precisely stated here. We have these assumptions, and we take a theta between 0 and 1/2. Then we can find an epsilon such that if U is a minimizing WSP harmonic map with this bound on energy, then we can go to a smaller ball and bound the fractional energy. This is the adaptation similar to the local case. This is the adaptation of the decay estimate. And this is exactly where we get the additional assumption SP close to N. So we'll see how. So when we look at the proof of the decay, so we prove it by a method of contradiction. That is, assume that is not true, then we can find a sequence of minimizers which do not exhibit the decay estimate, but which has the total energy very small, which is epsilon I to the power P. So there's a typo here. This should be UI. So we're looking at a sequence of minimizers, and we see that this converges to 0 as I tends to infinity. And now we define a sequence of normalized functions, VI, which is like here, and observe that these functions converge to a WSP limit V, which satisfies the PD here. So this is the fractional P Laplacian of V equal to G, where G is in LP prime, or P over P minus 1. So we need to use the regularity of this limit function to continue our result. And so the complicated part is that this is vector valued functions, and we have an equation involving fractional P Laplacian. And unfortunately, not many results were known about vector valued P Laplacian equations involving vector valued P Laplacian. And we state this as a conjecture that if not even this result when used in WSP and U satisfies P Laplacian of fractional P Laplacian of U equal to 0, then we don't even know if it's locally Hölder continuous. But there has been work done by, for the case n equal to 1 or scalar valued functions, there has been results about fractional P minimizers by Castro, Cusi, Palatucci, Mingjian, and higher Hölder regularity for the scalar valued function is also done by Brasco, Lindgren, and Shikora. So this was another difficulty which we faced, and therefore we have the addition assumption SP close to n. And if we know more results about the vector valued fractional P Laplacian, we will be able to improve the result to more general cases of S and P. And we talked about the case when we have the extension theorem into the unit sphere. So we can do the extension into more general manifolds, um, and then which therefore we can improve our result to more general manifolds. So this is the result that we are looking at. So let P be between 1 and infinity, S between 0 and 1, and omega is a bounded domain in Rn, and N is a compact smooth manifold of Rn with the homotopy groups up to order lambda minus 2 is 0 with some conditions on lambda, P, and N, and assume that we have a map which takes values in Rn and it goes into the manifold n outside omega. Then we can find a map U such that it takes values into the manifold with the same values outside omega as the original function, and the fractional norm of the fractional energy of U is bounded above by the fractional energy of V up to a constant. So here in the local case, extension theorems has been known, and here not that we have certain topological assumptions on the manifold, and this condition P strictly less than lambda less than or equal to n. This is the same condition as we have in the local case. So one thing that we were thinking about, this might not be an optimal condition. We would be able to get an optimal condition where this extension theorem would work. And happily recent works from Anton Detail, one of Shafjan's students, has proved recently that in fact this is the optimal condition, because when you shift to fractional case, we would expect that this should be something like SP less than lambda, not P less than lambda. But in fact, it turned out that this is the optimal condition, not the one we expected. And this is the main result that we have. That is, we have the same assumptions on the domain and the manifold coming out of the extension theorem. And we have this additional assumption, SP is close to n. If U is a minimizing WSP harmonic map in omega, then U is locally Hölder continuous outside a singular set with its Hausdorff measure of the singular set is equal to 0, and the dimension is strictly smaller than n minus SP. And this is if you're curious about more about these results, it's out on arXiv. And I would like to acknowledge my advisor, Dr. Arman Shikora and Dr. Kasama for their valuable discussions throughout this project. Thank you.
All right. Thank you very much.